Thank you. So I'm going to be talking about this paper, which you can find on arXiv here, and this is joint work with Ishan, Frederick, Andreas, Daniel, Albert, and Matthias. Some of them are here today. Okay. So I'll begin with a few slides of motivation for this work from the direction of Hamiltonian complexity theory. And I don't want to go into too much detail here, but I want to sort of highlight a few results from the last couple of decades, which have shown us that you can actually simulate many complicated Hamiltonians with very simple families. So here I just have a few examples which are taken from a large corpus of very nice results. But so first of all, in 2004, whilst proving the QMA hardness of the two-local Hamiltonian problem, Kempkataev and Regev showed a way that you can reduce three-local Hamiltonians to two-local Hamiltonians. And this was generalized in 2008 by Oliveira and Terhal, who showed that, in fact, you can take any k-local Hamiltonian for k greater than 2 and reduce this down to a two-local Hamiltonian, where now we can assume our simulator Hamiltonian is acting on a two-dimensional lattice. And more recent work has shown far more powerful results. In particular, this paper from Cubitt, Montanaro, and Piddock has, for example, shown that any k-local Hamiltonian on qubits can be reduced to just two local Heisenberg interactions acting on a two-dimensional lattice. So, and here I should reiterate, the idea is that we start with a very complicated Hamiltonian that we want to sort of understand the physics of, and we want to somehow reduce this to a simple Hamiltonian which somehow captures this physics. So the main tool that's used in all of these constructions are the so-called perturbative gadgets. But for the moment, I just want to make the point that these sorts of results seem extremely powerful from the perspective of analog quantum simulation, by which I mean, if I want to build an analog quantum simulator, then in principle, I only need to build some machine that can implement two local Heisenberg interactions on a two-dimensional lattice. And just by sufficiently tuning these, I get all of many-body physics for free. But there's a caveat with this, which was noticed, in all of these works, really, which is that this comes at a cost of unfeasible scalings. So in particular, when we start with our extremely complicated k-local Hamiltonian and reduce it down to a two-local Hamiltonian, we end up with a Hamiltonian from this simpler family, which may have extremely strong, which will be written in this kind of simple two-local form, but the individual terms will scale polynomially in the system size. And from the perspective of Hamiltonian complexity theory, this isn't really a problem because everything's just polynomial, so we don't care. But from the perspective of analog quantum simulation, this poses a huge barrier. Because if I want to simulate my favorite spin system, and I need to implement interactions that vary over dozens of orders of magnitude, this is never going to be feasible in practice. So this motivates two very natural questions that we can ask. Firstly, can this be avoided? Is this just a feature of these specific constructions that have been used? Or is this a more generic problem that we'll always run into when trying to make these reductions? And secondly, on the other hand, what can we say about the regime of scalable quantum simulations? So if we impose this additional restriction on our sort of simple simulating Hamiltonian, that the interaction strengths don't scale with the system size, and maybe that we only use a linear number of qubits in the size of the target system, what can we actually still obtain these such powerful reductions? And before I move on, I'll just quickly clear up some notation. So I'll use H to denote the Hamiltonian that we want to simulate. So this is the more complicated Hamiltonian. And for the simulator Hamiltonian and simulator system, I'll use H prime. So just think prime means the kind of simpler system, the system we actually want to implement. Okay. So in order to answer this question about whether these scalings can be avoided, we first need to understand where they're actually coming from. And to do this in this work, we first kind of generalize the notion of Hamiltonian gadgets that are used commonly in the literature. So here I've just got a sort of reminder slide of what perturbative gadgets are and how they work. And for this illustration, I've used the 3 to 2 local gadget from this paper by Olivieri and Terhal, which is just the simplest to draw, but there's, of course, many gadgets that use this kind of similar recipe. So the idea is that we have some 3 local interaction H acting on 3 qubits, and we want to somehow simulate this with a 2 local Hamiltonian H prime, acting on these 3 qubits, but then also some ancillary system. And we somehow want to construct this H prime so that it will capture the physics of H, even when we insert this gadget into a larger system, maybe consisting of more interactions. So the general recipe that's used for these sorts of constructions is that we start by adding an ancillary qubit to these 3 original qubits, and then, so this qubit we want to use as a sort of mediator which will mediate the interactions between the other 3 qubits. So we first apply this large energy penalty to the 1 state to kind of force this into the 0 state all the time throughout the dynamics. And so the low energy subspace of this Hamiltonian will kind of approximately just be the state where this thing's always 0. And then by using some relatively weak interactions, we can perturbatively create an effective Hamiltonian on these 3 qubits, which effectively looks like this 3 local term. Okay. So it's sort of obvious looking at this recipe that we're going to end up with unfeasible scaling. So I mean, this parameter delta, firstly, we need to scale this very high just in order to kind of improve the perturbative approximation. But just on a more sort of basic level, this delta needs to be larger than all of the energies in the system so that the ancillary qubit kind of stays in the 0 state. So we can ask, is there some way that we can kind of extend this recipe to a regime which maybe isn't perturbative? And to answer that question, we want to kind of first come up with a definition of what anything that looks like a gadget should satisfy. And then from there, we will define a sort of slightly more easier to work with definition. So yeah. So here I've written what we call the zeta epsilon gadget property. And this, in words, is just the property that you want any H prime that sort of gadgetizes H in this way to satisfy. So the idea is that we start off with this interaction H, which I've drawn as this 3 local interaction, like in the previous slide. But it may be part of a far larger Hamiltonian where we have a kind of capital H and lots of other terms in a many-body system. And we want to kind of replace this H with some H prime, which acts on the original qubits that H acts on, with the addition maybe of an ancillary system. And we want to do this in such a way that by making this substitution, the spectrum of our overall Hamiltonian is still kind of approximately right. So you can see here there's 2 error terms for the spectrum. Firstly, epsilon, which is kind of an absolute error, which quantifies how good the gadget is in isolation. And secondly, zeta, which is an error which is kind of extensive and scales with the size of the system. Yeah, so this zeta parameter sort of quantifies how well the gadget will combine with other terms. Okay, and this idea here is just sort of written slightly more formally up here. Now, this is a definition of a property that we want gadgets to satisfy, that they kind of ought to satisfy if they're doing the right thing. But it's not very easy to work with because, I mean, in principle here, to check that this is satisfied, we would need to check over all possible Hamiltonians on the larger system. We would need to kind of check over these unitaries to take into account the different ways that the eigenvectors can be rotated. So in the next slide, so this definition up here is just the gadget property from the previous slide, but stated a little more informally. But we also have this definition 2, which is of a zeta epsilon gadget. And this is slightly less motivated, as the other one was, but it's a far easier definition to work with, as this is kind of, this only relies on local properties of the gadget. So we say that H prime is an eta epsilon gadget for H if there exists some projector and some unitary, such that our unitary is quite close to the identity up to eta, and such that when we project H prime onto some subspace, we kind of approximate the spectrum of H up to epsilon. And so we have these kind of 2 notions of a gadget, one thing that's a property they ought to satisfy and one thing that's kind of an easier definition to work with. And these two theorems just reassure us that these actually kind of are in agreement. So firstly, I have theorem 3 saying that anything that looks like a gadget and satisfies this gadget property, anything that is a gadget and satisfies definition 2 will also satisfy definition 1. And we also have this theorem here, which says that anything that looks like a gadget in that it satisfies this property will satisfy definition 2. Okay, and up to some unfortunate square root of some of the parameters. So with this definition of what a gadget is kind of in general in mind, we can then think about proving their general properties. And to do this, we just start with some very natural things that we expect them to satisfy. Oh, whoops. Okay, in particular, we start by showing that you can combine these gadgets in a sort of parallel way. And these sorts of combinations have been used in kind of ad hoc constructions in Hamiltonian complexity theory for a while. But we're just showing that this is sort of possible in general with our definition. And in that way also getting some reassurance that our definition is maybe a sensible one in that this all works. So what this theorem says is that for H, k-local Hamiltonian with lots of terms hi, if we have a gadget hi prime for each of these local terms, and we just replace each of the terms in our original Hamiltonian with their gadgets, then this entire system is a gadget for this system. So we still kind of maintain this approximate spectral relation. Okay. And also we generalize a result from a paper from 2008 saying that even if the interactions in this gadgets are bounded strength, H prime can still approximate the ground state energy to just an error that scales with the size of the system. So, and again, these are not necessarily very surprising results. They're just generalizing lots of constructions that are already known and showing that, our definition at least works in some sense. So now I come on to the maybe more kind of relevant property of gadgets from the perspective of why we were studying them in the first place, which is this theorem which tells us that energy scalings for gadgets really are sort of an unavoidable consequence of just making these reductions. So this theorem is saying that if I have H just an interaction which is a k-fold product of Pauli terms, so this is a k-local Hamiltonian term. If I have any gadget H prime, which is an eta epsilon gadget, this is our definition 2, where H prime is k prime local, so k prime less than k. So we're sort of simulating the H term with a term of lower locality, then the norm of H prime must scale like eta to the minus 1. And so why does this mean that we have energy scaling? If you remember, this parameter epsilon sort of corresponded to the absolute error in the gadget, and eta here corresponds to the kind of extensive error. So if we have a system of size n, then we will end up with spectral error that goes like eta times n. And in particular, this means that if we want to control the spectral error, we'll need to scale eta like n to the minus 1, and we end up with the norm of H prime scaling like n. Okay. So this kind of provides us with a no-go in some sense in terms of telling us that these sorts of reductions using gadgets will never give us a way to sort of scalably reduce the locality of Hamiltonians. But if we want to kind of get around this if we want to get around this, we can consider sort of broadening our definition of what we expect from an analog quantum simulator. So up until this point, I've kind of been working with this definition that's really come from Hamiltonian complexity theory, where we want to sort of approximate the spectrum of our Hamiltonian in this quite rigid sense. But in practice, from an analog quantum simulator, we just expect to be able to get out expectation values of observables. So what we might ask from a quantum simulator instead of these spectral conditions is just that for some set of observables, we can accurately reproduce the expectation values. So what I've got on this slide isn't really too deep. It's just writing down what you kind of expect a analog quantum simulator to be doing. So we have some encoding phase where we have our state on our target system being sent to a state in the simulator system, some evolution phase, which will include some quantum channel, TT, and some also observable encoding, and a measurement phase where we measure the encoded observable on this evolved simulator. And to say that this simulation is good, we just want to say that the expectation value of this measurement is within, say, epsilon of the kind of correct expectation value. So the value of our observable O on the correctly evolved state on the target system. Okay. And yeah, something I should maybe mention is that obviously this is an extremely general form of a simulator. I've just written down a quantum channel TT, but we could think about including dissipation in our simulation, maybe in errors in our encoding or measurement, maybe kind of deliberate dissipation, as I'll come on to, and maybe also modeling the noise in the simulator. And so with this more kind of broad notion of what analog simulation is, we can think about new ways to kind of try to solve this problem of reducing locality. And before I come on to that, I just want to quickly remind you sort of this 3-to-2 local Hamiltonian construction. And if you remember, the large scaling was necessary because we had an ancillary qubit which had to be kept in the zero state by this extremely strong interaction delta, which ended up really needing to be larger than all of the energies in the system. But if we're allowing a sort of looser sense of simulation and dissipation in our system, then we could think about trying to just force this ancillary system into the zero state by repeatedly applying a decoherence channel and exploiting the quantum Zener effect, so that with high probability, this qubit will stay in the zero state, and meanwhile the other 3 qubits will kind of undergo some other evolution. And this next slide is just kind of putting this into words. I mean, this is completely unreadable, but there's a nice picture that you should look at, which is that we start off with our kind of our target system here, which is H, and we have this ancillary qubit A. And the process is that we can apply some Hamiltonian H prime for time delta t to kind of evolve this into some superposition of states where the ancillary qubit is in the zero state and also where it's in the 1 state. And then we can apply a decoherence channel onto the A qubit, which sort of collapses the A qubit back down onto the zero state with high probability. And the result of this collapse is that the sort of target system undergoes evolution as if it had evolved under a different Hamiltonian H. Okay. So in particular, I'll mention that this can be used to reduce k local interactions to k over 3 plus 1 local interactions, which as a special case, this gives us a new 3-to-2 local gadget. And also I should mention that in this Hamiltonian, this simulated Hamiltonian H prime, we do require the terms to scale with inverse of the step size, but this step size doesn't need to scale with the size of the system if we're just using one gadget. So if we're just using one gadget, then this kind of gives us an improvement over the no-go theorem that we arrived at for the pure Hamiltonian gadget case. However, this doesn't completely solve the problem, because if we use multiple of these gadgets in parallel, then we'll need to scale delta t down sufficiently to ensure that the errors are controlled, and this will incur at least a square root scaling in the size of the system. Okay. So what have we done? We've shown that for the sort of pure Hamiltonian framework of analog quantum simulation, if you want to apply these sort of gadget techniques to reduce your Hamiltonian's locality, then you'll run into these unavoidable barriers that prohibit kind of scalable experimental implementation. And on the other hand, we've shown that if you can slightly loosen your requirements for a quantum simulator and just require expectation values and maybe exploit open system dynamics, then you can actually get around these constraints somehow. But there's still lots of questions that this doesn't answer. Firstly, for example, can we do better than this? I mean, as I mentioned, we still have some scaling, which is an improvement on the 3-to-2 local scaling in the pure Hamiltonian case, but this still doesn't completely satisfy our initial aim of creating a scalable quantum simulation. I mean, on the other hand, we can ask, what are the limitations in this looser framework for simulation? So we probably shouldn't expect that if we still impose these scalability restrictions, require sort of constant strength interactions, we shouldn't expect that we can still obtain all of many-body physics from very simple models. But maybe we can do a little better than in the pure Hamiltonian case. And yeah, and maybe perhaps there's some sort of resource theory that would arise of different simulators related by their simulability. Okay, I think, yes, I have no summary. That's it. Thank you.
All right. Thanks for the nice talk. Do we have questions?
Excuse me. Thank you for the very, very interesting talk. So my question is, in your sort of this dissipative Gaussian simulation framework, which doesn't reproduce the spectrum, it reproduces observables. Do the observables have to be local? Because I guess in some physical systems, like if you care about topological order, you need to measure some non-local observables. So can you comment on this?
So I mean, in the way that I've outlined it here, and just I've sort of kept it very general. I mean, in general, these observables that we might be interested in could come from a subset of the full space of observables on the target system, but we could reduce to local observables and say that our simulator only needs to capture these. But yeah, I mean, this is something that's sort of left general here, and does that sort of answer the question?
I think we have time for one more question, perhaps.
Thanks for the talk. Did you also think about using something like mid-circuit measurements and adaptive like processing instead of these dissipative evolutions?
So a little bit, yes. But the problem with doing this is that we have this kind of general simulator that we allow dissipation. And if we start using mid-circuit measurements and adaptive evolution, then suddenly we're doing full fault-tolerant quantum computation. So I think kind of a reasonable restriction to impose on these sorts of channels is that you don't kind of do any sort of mid-circuit readout and don't need to adapt the simulation.
We might still have time for a quick question. Okay, if not, then please let's thank the speaker again.